Okay, today is going to talk about get into welding of steels, and I thought maybe one way to put this in perspective is to go back to how welding, as we know it today, actually got started. It was in the 1850s. Sir Henry Bessemer learned how to melt steel by essentially preheating the air coming into building a vessel where the air got preheated, so he could get high enough flame temperatures. And then Andrew Carnegie came around in the 1880s, and he started what's now the successor company is USX, which used to be US Steel. And Andrew Carnegie became the richest man in the world by selling steel for railroad rails and things like that back in the 1880s. He was essentially the Bill Gates of his day. But it wasn't until the 1880s that arc welding became a beginnings of a commercial process. I don't know if I already mentioned this before, and maybe it's in the other tapes, but Sir Humphrey Davy in around 1807 actually discovered the electric arc. He basically had a bunch of Leyden jars, which are a bunch of little batteries. You know, it's basically an electrolyte with a couple of metal plates, dissimilar metal plates, so essentially made a cell. And they call these things Leyden jars, L-E-Y-D-E-N. And he put some of these together. He got a high enough voltage and a big enough current that he actually put two electrodes together, pulled them apart, and he got an arch of flame across there, a plasma arch. And he called it an arc, okay, because it would form this arch. And basically because it's a hot flame and hot gases rise, and so the flame between the two horizontal electrodes was rising, but it has to be attached because the current's going through it, attached to the ends of the electrodes, so it formed a little arch there, okay? And that's where we get the term arc. The problem was that was never used until the 1880s when Edison and Westinghouse came along and started providing a source of electricity. I mean, you didn't want to have a room full of Leyden jars to do electric arc welding, although there actually is a woodcut from France in the 1870s where they had a room full of Leyden jars, and they had some people doing arc welding in the 1870s with a bunch of Leyden jars. But, you know, that was not exactly, you know, can you imagine some guy, you know, with his pickup truck with a bunch of Leyden jars on the back of it going to weld something in the field, right? So it really wasn't until the 1880s when you had electric generators and Westinghouse and Edison. And the problem then was all they had was bare steel electrodes, bare steel wires. And if you actually weld with a bare steel wire, you'll end up with Swiss cheese for a weld, because there's nitrogen in the air, and the nitrogen dissolves in the liquid steel, and when the steel solidifies, it rejects the nitrogen. Solid iron does not dissolve as much nitrogen as liquid iron, and so the bubbles of gas come out, just like, you know, CO2 comes out of your soda when you depressurize it by opening it up. Well, by dropping the temperature of the steel, the nitrogen comes out just like the CO2 bubbles in your soda coming out, and you end up with Swiss cheese in your weld. And so they weren't the best quality welds, but people did weld. And then two things happened in different parts of the world. In Sweden, Göteborg, Sweden, some guy was welding with a bare electrode, and he found that if he stuck his electrode in the mud and welded with a muddy electrode, the Swiss cheese pores went away. And that was the beginning of what we now know as the ESAB Corporation, ESAB, okay? And that's also what's known as flux-shielded welding or mineral-based electrodes. This is a 7018 welding electrode, and now instead of just sticking it in the mud, this is a very specially formulated material made out of all kinds of fancy things like limestone, silica, iron oxide, manganese powder, okay? Very proprietary compositions. Every company has kind of their own special compositions. The 7018 number on here actually is a shorthand for E7018, which is the American Welding Society designation. And the 70 means it has 70 KSI tensile strength, and the 18 and the 1, or the 18, tell you other things about the type of flux coating, the type of position that you can weld in, overhead, horizontal, flat. Not every electrode works in every position. Yeah. But which depends? Yeah, vertical. Yeah. There's a I believe this number, so there's a 7028. Well, a 1 usually means it can be used in all positions, okay? But a 2 restricts you to certain positions, and you just can't weld in certain other positions. The arc is not stable in those other positions. It also has, these things have secret alloying elements in them. Turns out the Lincoln Electric Company likes to use a little bit of barium. It stabilizes the arc, because barium, if you look at it in the periodic table, it's down in the lower left-hand corner. And those elements tend to give up electrons easier than anything else. And so it tends to stabilize, give off electrons easily. And so it tends to stabilize the arc. The problem with barium is it has a very low toxicity level. And so they have to do some other things to keep the vapor pressure of barium down in those. But anyway, that's in Göteborg, Sweden in the early 1900s. They learned to weld with muddy electrodes and they got rid of the porosity. In the meantime, in the United States, and I don't know, I've never heard who it was, but some welder found that if he wrapped a piece of paper around the bare steel, he got rid of the porosity. And that's the beginning of the cellulosic series of electrodes, where basically you use cellulose fiber and other minerals such as silica and titania, TiO2, and things are put in these cellulosic electrodes. This is a 6011. Whoops. 60 means 60 KSI tensile strength. The 1 means all position, and the other one tells us that it's, I think, can't remember if sodium or potassium based for the arc stabilizer. Now the cellulosic electrodes, basically cellulose is C2H, or no, it's not C2, it's CXHYO something, okay? It's carbon, hydrogen, and oxygen. It's basically a starch, which is similar to a sugar, but not exactly the same as a sugar. But it has lots of hydrogen in it. And so the difference between this electrode, the 7018, this is called a low hydrogen electrode, and this is just a regular electrode, or sometimes people call it, they can say high hydrogen. This is called low-high a lot of times, just as a, trade name, or not a trade name, but a jargon. This is a cellulosic or hydrogen-containing electrode. This one actually keeps the nitrogen away by burning up the cellulose. At those temperatures, you actually end up with an atmosphere that's 60% hydrogen from decomposition of the cellulose fiber, and the rest of it is carbon monoxide, water, and a little CO2. So you end up with, this generates its own atmosphere. This actually generates an atmosphere, although the literature doesn't usually tell you that, but the silica and other things in here actually form silicon monoxide, just like carbon monoxide. Well, if you look at the periodic table, silicon's right below carbon, and so you actually form silicon monoxide. And other things, but there's very low hydrogen in this. In fact, this one has to be baked out. This one is baked at about 300 degrees Fahrenheit to harden the stuff. They basically extrude this on. It looks like cement, wet cement, and then they extrude it on and they bake it about 300 degrees. To dry it, this one is baked at like 600 or 700 degrees. This one you just leave in the air and it's fine. But this one could have, well, it has the equivalent of 60% hydrogen in it. This one, you want to keep the moisture content very low because you're trying to keep the hydrogen low. Typically, you analyze these for their water content, and you want to be less than 0.2% by weight of moisture, which is pretty low, which usually means you stick these in an oven at like 300 or 400 degrees. If you go to the shipyard, they typically will only allow these out of the oven for about 4 hours. Different specs for different steels. Yep. Yep.
The low hydrogen is the
This.
welding, yeah.
Yep. Yep.
For inox welding, is that right?
Inox?
Inox, yes.
What's inox?
High quantity of nickel or titanium steel.
Oh, alloyed steels, you can go, they have 80 18s, 80 13, they have 90, they have 100, 110, and they used to make, I don't know if they still do, 120. So there are various other versions of these that go to, for example, if you're welding HY80, you might be using 110 18 or 118 electrodes, okay? And they have more nickel and other things in them.
A low hydrogen.
If it has the 8 on the end will usually mean low hydrogen. In general, the only cellulosic electrodes, not all of your E60 series are cellulosic, but most of them are. And they produce a lower strength weld deposit for just your garden variety bridge steel or something like that. I have seen E7011, which would be is a cellulosic 70 KSI electrode, but you don't see it very often. Everything above 80 and above is low hydrogen, because once you get, and we're going to talk about that, once you get to those strength levels, hydrogen cracking gets to be a serious problem. Okay, and that's actually part of the history that we're going to talk about here. Is now we're up to the around 1900. By the way, this is a bigger manual electrode, one of the biggest ones. This little one might be running in the 125 amp range. This one's a little bit bigger. This is an 1/8 inch. This one's, or that's 1/8 inch. Actually, these are both 1/8 inch, because this has a heavier flux coating. But they come in different diameters, defined by the diameter of the core wire. And so this one may be 150 amps or something, or 125. This one is more like 2,000 amps or 2,500 amps. This one is not used by a human. You can actually clamp this into a machine. And this type of electrode is used for repairing ingot molds in a steel mill. And all you're doing is you kind of build a mud dam up against, actually you do more than mud, but basically you build a ceramic dam up against the side of a crack in a great big ingot mold, and you have a machine with 2,500 amps just slowly lowers this in there and just melts everything. Just a great big electrical short, if you will, and it just melts the steel in there. In fact, this is weld mold, because it's basically welding up molds. Okay, if you want to pass that one around, you can. Or you can come and look at it at the break. So we ended up with what's called often stick electrode welding, manual metal arc. The real name for the American Welding Society is shielded metal arc welding, SMAW. And in fact, in World War I, the government formed the Emergency Fleet Corporation, because they had to get the boys over there to Europe, right? And they had to build a bunch of ships to take the soldiers over. And so they had to start building a bunch of troop ships. And the head of the Emergency Fleet Corporation was a guy named Comfort Avery Adams. He had been a professor of electrical engineering at Harvard University. He basically had worked in designing welding power supplies and stuff. Remember, it was only in 1880 that you actually had Edison and Westinghouse come along and kind of using transformers. In fact, that was why Westinghouse beat out Edison for using AC versus DC current. DC, you can't use transformers, but with AC, you can have transformers to change your voltages, and that's why Westinghouse was right, and that's why we use AC power, because you can transform the voltages easily with transformers. Well, that same type of transformer technology, professors of electrical engineering basically were designing things like welding power supplies in the 1890s and 1910s. And Comfort Adams was that type of electrical engineer. He was a professor at Harvard. From 1914 to 1917, he was jointly a professor with MIT, because MIT and Harvard tried to merge at that time, and the Supreme Court of Massachusetts turned it down. Have I told you this story? No, maybe we'll do it at the break. It's too long a story, but 3 times Harvard tried to purchase MIT. And finally, after 1919, they decided they gave up and started their own engineering school, which is now known as the Harvard Business School, but we can tell you that story later. And Andrew Carnegie gave Harvard well, I might as well tell you the story. MIT started across the river in Copley Square in the 1860s. Within 10 years, they were kind of outgrowing the space, because they were landlocked by all the other things that were over in Copley Square, and they wanted to grow. And so the president of MIT and the president of Harvard got together, and there was an agreement like 1873 for Harvard to purchase MIT and move them up towards Harvard. And that fell through, and then there was another time, I think it was the 1890s, and then in around 1910 or something, there was a third agreement. The final time, Well, it turns out Andrew Carnegie gave $100,000 and some other people gave some money, and they purchased some land right across from Harvard Square over in Allston, which you now know where the Harvard Business School is, purchased that land in order to be able to move MIT up there. But what happened was, first the MIT faculty voted it down, and they determined that they'd rather go out of business than be part of Harvard, I guess. Is one way to look at it. The Supreme Court of Massachusetts said Harvard could not use the Gordon McKay trust funds. Gordon McKay was a shoe merchant in Boston, and he had given $10 million to Harvard University in like 1910 or something to start a school of applied science. And $10 million back then would be like, you know, $250 million today. You know, people talk about these huge grants to universities. Well, that was a huge grant to the university. But the Supreme Court of Massachusetts said the agreement was such that they couldn't use those funds to actually purchase MIT. And so they weren't able to purchase MIT. Arthur Amos Noyes, who was one of the professors, he was a chemistry professor here, but he had become president of MIT, and he was a big, he had a big conflict with William Walker, who was the founder of chemical engineering. And chemical engineering was sort of invented by Arthur D. Little and William Walker here at MIT. Arthur D. Little was not a professor. He had graduated, and he went off and started this consulting company, which just went bankrupt, right, a couple of years ago. In any case, William Walker is Walker Memorial. If you go over here to the lousy cafeteria, you know, that's Walker Memorial. Anyway, Walker and Noyes were, one was a chemical engineer, and Walker wanted to have close ties with industry. He started a chemical engineering practice school at MIT, which is one of the most successful things we've had for the last 100 years. Noyes was very much against doing anything with industry. That would pollute academia. And so, anyway, Noyes became president of MIT, tried to work out the agreement with Harvard, got rebuffed, and he left MIT with Millikan from Case Western Reserve, which was Case Institute of Technology back then. Millikan was the first American Nobel laureate in physics for the Millikan oil drop experiment, do you remember? Okay, where he measured the charge of an electron, or showed that it was quantized. And they went out to California and a little school called Throop Institute of Technology. Anybody know what Throop's called today? It's called California Institute of Technology. It's in Pasadena, and they founded Caltech. So Caltech's a spinoff of MIT. In the meantime, MIT had started building these buildings you're in. This building, or this set of complex of old buildings, was the second largest building in the world at the time it was built. And MIT was bankrupt. That was one of the reasons they agreed to sell to Harvard, or the president did. An anonymous donor gave them $6 million, which was not quite what the other guy gave them. Later it was found out that anonymous donor was George Eastman of Eastman Kodak, and that's why Building 6 is called the Eastman Building, which is one of the last buildings built. So MIT was out of bankruptcy. Harvard still didn't have an engineering school, so they took the land and they built their engineering school, which was the Harvard Business School, as we know it today. But if you look back, the Harvard Business School had people like Frederick Taylor, the father of scientific management. He did industrial engineering, time and motion studies over at Watertown Arsenal, which no longer exists. It's now a mall, right? But he did time and motion studies of, you know, people on the factory floor. So Harvard Business School was Harvard's engineering school originally. So anyway, that's sort of an aside. It's sort of an interesting story. I don't know what it means to the people that take this at other universities, but oh well. At least you now know where Caltech came from and why Harvard and MIT have this rivalry. In any case, getting back, this is shielded metal arc welding. After World War II in 1921, or is it 1919 anyway, somewhere around there, Clifford Avery Adams, who had been head of this Emergency Fleet Corporation, and realizing that we needed better science and technology in welding, founded the American Welding Society. Still, people were not using welding for really critical applications until the early 1930s, and the Big Inch pipeline, which was a 30-inch gas pipeline from Louisiana to New York or New Jersey, was built by welding. Now that's a critical structure. I mean, if those welds break, you have gas coming out and you have a big flame. So that was probably one of the first critical structures. And then welding really took off in World War II when they started building the Liberty ships and other things. And since then, it's kind of grown. Patented, I think it was 1936 or so, what they call the union melt process, which we now call submerged arc welding. In submerged arc welding, you have a steel plate here, you have an electrode here, and instead of the flux being wrapped around the electrode, you basically just have this layer of what looks like sand, flux, and the arc is submerged beneath the sand. That's why they call it submerged arc. You don't see it. All you see is little gas and bubbles come up every, gas bubbles, smoking every now and then. But most of you seen submerged arc welding in a shipyard or something? Okay. And it turns out there's a letter from Franklin Roosevelt to Churchill in like 1943. He talks about the wonderful productivity of this new welding process. He didn't call it union melt, but we think he's talking about submerged arc welding, because it lays down metal about 5 or 6 times as fast as the old stick electrode process. In the 1940s, actually right before that, in the late 30s, the Naval shipyard in Philadelphia brought over some French technology because they were trying to weld aluminum airframes. And they basically invented or perfected in the 40s a process called gas tungsten arc welding, where you have a tungsten electrode that's not consumed, and you just have an argon, or nowadays in the United States, helium, shielding gas. Most of the rest of the world doesn't use helium because helium is expensive in the rest of the world. It's not expensive in the United States because the United States has like 98% of the world's reserves of helium out of a bunch of oil wells in Oklahoma and Texas and places like that. It turns out some of these oil wells, or not oil wells, but gas wells, have like 2 or 3% helium in them. And so we basically just pull helium out of the ground with the natural gas, and everybody else has to liquefy air and take it out, and it's very expensive. So liquid helium in Europe costs about 5 times what it costs in the United States. Here it's like $2 a liter, and we just blow it off in the air. But someday we'll have to get it out of the air just like everybody else when our gas runs out. Anyway, we got about another 100 years before we have to get helium just like everybody else. It stays on the Earth, it's just gets diluted. So gas tungsten arc welding is a great process for welding aluminum. And then in the 1950s, some guys at a company called Airco, Air Reduction Company, invented what's called gas metal arc welding, where we go back to the bare steel wire, a continuous wire being fed in, but now you have an argon shield of gas to keep the nitrogen away. And it turns out, 25 years ago, about 60% of about 50% of the welding was done by shielded metal arc, and about 30% was done by gas metal arc, and then the other 20% was all kinds of other processes, whether it's laser electron beam, submerged arc, gas tungsten arc, or whatever. Nowadays, about 50% is gas metal arc, 30% is shielded metal arc, and you still have the other 20% is all the other processes. Gas metal arc lays down metal about 3 or 4 times as fast as shielded metal arc. The problem is the gas metal arc requires bottles of gas, requires a wire feed. It's more expensive equipment. It actually can generally produce as good a weld as shielded metal arc. Shielded metal arc is the choice in the field because all you need is a power source. You don't need bottles of gas, things like that. There are versions of gas metal arc which are called self-shielded metal arc. It's been invented by Lincoln Electric Company in the early 1960s when they came out with it. Self-shielded metal arc, or actually self-shielded, the true name is, it's a form of flux core arc welding. I think then they put that CSS for self-shielded. I'd have to go back and check how AWS does it. But basically, you have a tubular electrode rather than a solid electrode, and you can either put your flux on the inside of the tube and essentially invert some shielded metal arc, and essentially have a flux to help with your shielding process and stuff. Or you can actually put, for steel, you can put aluminum powder inside the core of this tubular electrode, and the aluminum forms aluminum nitrides and keeps the Swiss cheese from forming. Okay, so this whole nitrogen problem we started out with in 1880, people are still working in 1960 on how to avoid the nitrogen problem in the Swiss cheese of the welds. Well, you know, the nitrogen problem's pretty well solved. I've probably only seen 3 or 4 nitrogen Swiss cheese type of welds in my career, because we really know how to control it. But that's not the real problem. The real problem that showed up in a big way in World War II and just after was hydrogen cracking, which is still a major problem. Okay, so the old shielded metal arc, particularly cellulosic, you're welding in an atmosphere of 60% hydrogen. These others, submerged arc, gas tungsten arc has very low hydrogen. Gas metal arc has very low hydrogen because it's just argon shielded. The flux processes, if they pick up moisture, will introduce hydrogen. Hydrogen cracking, a lot of times you just draw a Venn diagram. You have to have 3 things to get hydrogen cracking. You have to have hydrogen, you have to have stress, and you have to have a microstructure of the steel that is susceptible. And that usually means the higher the hardness or strength, the worse the hydrogen cracking is going to be. So we can use a 6010 electrode on 36 KSI yield steel, which is A36 garden variety building or bridge steel. I have a 60 KSI tensile strength, and I think the minimum is 52 KSI yield strength on that 6011 electrode. And that means that the welding electrode on 6011 is actually substantially stronger than the 36 KSI yield strength or 40-some KSI tensile strength.
What does TIG welding fit into this?
TIG is GT800. The official name in the United States is gas tungsten arc. The Europeans call it tungsten inert gas. Here's the T is the same T. And this one in Europe, they call metal inert gas, is what the Europeans call gas metal arc welding. Okay, so MIG welding is the same as gas metal arc welding. These are the official names in the United States. The US definitions are actually more precise than the Europeans. The problem with MIG is the Japanese solved it.
They always call it TIG welding in the shipyard.
Yeah, but they always call it stick welding too.
Yeah.
They don't call it self-shielded, or they don't call it shielded metal arc. So we call it by these common names, but the official names are these other things. The Japanese solved the MIG welding problem, metal inert gas. Well, one of the gases they use in shielded metal, in gas metal arc, is 100% CO2. Well, it's not inert. CO2 decomposes to carbon monoxide and oxygen and reacts with a weld pool. It can burn out 0.5% silicon out of your weld deposit. So it's not exactly inert. So the Japanese call it metal active gas when you start using CO2. So the Japanese will say MIG or MAG. The Europeans would just call it MIG and don't worry about the word inert. And the US uses gas metal arc welding. If you want to know why the US is so precise, it's because it's a Harvard grad named Halleck Campbell. Halleck passed away a few years ago. But well into his 90s, he was a consultant with the American Welding Society, and he had studied engineering at Harvard, and he was, he was quite a stickler for certain types of words. For example, in the early 1980s, I published a paper said a study of parameters and blah, 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 blah. I was over in Tokyo working for the US Navy in 1984 and 85. I get this letter from Halleck Campbell saying I misused the word parameters in the title of my paper. So I go to the Unabridged Dictionary and I look up parameters, and here on the 4th definition of parameters was the way I had used it. And you know how dictionaries will give you a sentence example? This particular sentence came from P.W. Bridgman. P.W. Bridgman was a professor at Harvard who studied high pressures, and he had used parameters the same way I had. So I write it back. I write back Halleck, and I say, "Dear Halleck, I explained all this to him, and he writes back, just writes a note on a copy of my letter. He says, "Bridgman, how could you?" Because Bridgman was using it in a way that Alec didn't want. But nonetheless, Alec, being sort of a liberal arts welding engineer, was a stickler for terminology. And so it turns out the American Welding Society terminology, all because of how it came, is sort of in some ways more precise than the rest of the world, for whatever it's worth. But then you get out to the shipyard and practice, and people talk TIG and MIG and stick and, you know, all kinds of stuff like that. So all kinds of different jargons in the trade. Okay, so hydrogen cracking is a big problem. They have lots of hydrogen cracking problems, a lot of Liberty ship problems for hydrogen cracking, where you have an initial flaw and it would grow over time. The insidious thing about hydrogen cracking is sometimes called delayed cracking. Because the hydrogen will diffuse around just like CO2 does in your soda at room temperature. In fact, I like to use that example. If you pour out a soda in a glass on the table and you come back 24 hours later, it'll be flat. The CO2 will have all dissolved out. A typical weld, let's say an 1/8 inch or 1/4 inch weld, you weld it with hydrogen, or you a cellulosic electrode, or a wet, low hydrogen electrode, one that's not properly dried and warm, and you come back 24 hours later, the hydrogen is gone. The problem is, it may have cracked in the meantime. Typically, what happens, the hydrogen is uniformly distributed when it first solidifies, relatively uniformly distributed, but then it will migrate, just like the CO2 can diffuse around. It will migrate to imperfections in the steel. So if I have a big inclusion or I have a stress concentration in a notch, it will go there and it will lower the cohesive strength of the material and cause a crack. Yeah.
There is no any evidence that we can base and say when the percentage of the hydrogen decrease this amount, then we have the beginning of the cracking.
No, it's still pretty empirical. I mean, I'll give you some numbers. I'm the only person I know that will throw out these numbers. I mean, you cannot go to the literature and find quantitative numbers about how many parts per million of hydrogen.
It is obvious that this is empirical still. I mean, that you can say that this percentage, maybe we have a big probability of a mistake, of an error,
right.
But we can say that this starts.
We know how to stop it, but it's kind of, you try to do all these things and make sure you're on this side of the field and you don't get over here.
And something else?
Yeah.
Do we want to have slowly diffusion of the hydrogen or rapidly?
Well, I'm going to talk about that. It turns out at low temperatures, below 0 degrees Fahrenheit, hydrogen diffuses very slowly, and you actually can trap hydrogen. I know a case where there was a hydrogen crack up to a year later, or 8 months later, because it was frozen in the High Sierra Mountains for most of the year. And so the hydrogen actually got trapped in there and actually showed up as a delayed crack months later. And because it was trapped, it basically was frozen. When we do hydrogen tests in the laboratory, we basically, because you're going to lose your hydrogen, we actually quench it in we put the sample in liquid nitrogen. And then you can wait a week or 2 weeks or whatever you want to study the hydrogen because you've frozen it in. It turns out at temperatures above room temperature, the hydrogen doesn't do as much damage because it tends to want to remain uniform and spread out rather than collect around these defects. It turns out right around room temperature, let's say between 0 degrees and 100 degrees Fahrenheit, is absolutely the worst range of temperature for hydrogen cracking. But that's the world we live in, okay, unfortunately. And because of these differences in diffusivity and how long it will stay there, most people won't quantify and give you hard numbers on how much hydrogen is enough. They will tell you that the shielded metal arc electrode has to be below 0.2% moisture, okay? And the Navy on some of the higher strength steels like HY100, I think has lowered that to less than 0.1%. But you really can't get it down consistently any lower. Of course, there have also been studies that I've heard are classified, but not having a clearance, I wouldn't know, that in a shipyard, if you're in a very humid environment, well, just the moisture, the humidity in the air I mean, you don't have to have moisture in the electrode. This stick electrode doesn't have anything shielding the moisture in the air. And at 75 degrees Fahrenheit and 100% humidity day, 5% of the air is moisture. You know, we talk about 20% 20% oxygen and 78% nitrogen and 1% argon and everything else is 1%. That's for dry air, 0% humidity air. But if I actually start talking about 100% humidity at 75 degrees F, if you look at the vapor pressure tables for the steam tables, you'll find 5% at 75. At 100 degrees, I don't remember what it is, but it might be 10% at 100% humidity. That's why if you go out on a 100-degree day and it's 100% humidity, you can sort of feel it in the air, okay? 10% of that air is wet, okay? So guess what? If you weld on a hot day, in a humid environment, then you will pick up moisture greater than the 0.2% of the low hydrogen electrode, just from the moisture in the air. Anybody have an idea? Actually, you guys may have clearances, so if you have an idea, you can't say it. What fraction of the time in a typical shipyard? Shipyards tend to be in humid areas. There tends to be water around shipyards, usually. It turns out, I've heard that over 80% of the days that we weld in a shipyard, we are exceeding the allowable levels for humidity and temperature for stick electrode welding. That doesn't stop us from doing it, but if you do a scientific study of what should be allowable, and with an adequate safety margin, 80% of the time we exceed that.
So when they do the majority of the larger hole welds at night?
It could be, I don't know. I don't, it's possible, but it may be, because it's lower temperatures and lower, maybe hopefully there's more humidity. I don't know.
Think about this. Is this moisture getting in because it's from the time when they take it out of the oven or whatever, it's intruding into the...
Now this moisture in the air is
the
just,
atmosphere.
you're actually striking an arc, and there's air there, and some air will be entrained into that arc. You haven't gotten to the rest of the tapes, but when I get to arc physics, I'll talk about plasma jets and how actually at the tip of an arc, if you have an electrode up here, you have an electromagnetically driven flow, and you have a jet coming off the tip of that electrode at about 500 miles an hour. Okay? It's electromagnetically driven. I'm not going to go through it now, but it's in the other tapes that you'll see in a few weeks. But you will entrain some of the air into this space. If that air has a lot of moisture, you're going to end up forming monatomic hydrogen that will get into the steel.
So no matter what, even if you're playing with inert gas.
Oh, if you shielded this with an inert gas, you can keep it out. Okay? I mean, if I go to gas mill arc and I'm using dry argon, there's no moisture there, that's not the problem. And a lot of what we do in the shipyard now is gas mill arc. But stick electrode still has the problem.
But Thyssen, the big company, the German company, has produced a new system of welding that is inside a water bath with plasma. How they do that? I mean, we are talking about 5 or 10% clear water in the air. We're talking about 100 or 200%. I mean, inside the water bath.
Well,
how can it prohibit? I mean, this kind of.
They are welding essentially with the cellulosic electrode in that particular case. Now, they are using steels that are very low in carbon content.
Yes, sir.
Because they go into these accelerated cooled steels, these thermomechanically treated steels, and those steels, at the strength levels they're dealing with, like 50 KSI, probably is the maximum strength level, it's almost impossible to hydrogen crack those. You can't get enough stress.
This factor is low.
Okay, it's a combination of all three of these. Okay, and if your strength is low in your material, the maximum stress you can get in a 50 KSI material is 50 KSI, and that's the maximum residual stress.
So if we are looking at this map, we want to go to the edges, not in the middle, because if we are in the middle, we are moving in the middle, where we have overlap, then we are in dangerous area.
Right. It's actually the combination of all three. You have to have all three.
So if you eliminate one, then you decrease the probability that you will have a crack due to...
Absolutely. To give you an example, back, this was like 1978 or 79. I was a young assistant professor. And I didn't know that much about welding. I know more now than I did then about welding. But I get a call from a shipyard over here that was repairing a destroyer. the destroyer was supposed to be done within like 3 weeks, and it's been in dock for 6 months, right? But they had taken out the boilers, and they had these chrome aluminum steels, boiler tubes, and these have very high hardenability, so they will give you a super hard microstructure. And they had to weld those to carbon steel in the transition in the cooler parts. And they had been working for 6 weeks to make this weld. And what they had, got a tube, and these are like 1-inch diameter tubes, they might have been an inch and a quarter, I don't remember exactly. But you got these tubes of chrome moly steel, carbon steel, this is your center line, right? And they were putting in what they call EB inserts. And EB insert stands for electric boat, okay? An EB insert is nothing more than a piece of round wire that they milled corners out of, like this. They milled that corner and that corner out of the wire, and they put this in on the inside of this pipe, a little ring in there, so that when you come in here, you melt that insert. The Navy spec said you had to use a stainless steel insert and not an Inconel insert. Inconel is a nickel-based alloy. These guys, they had people come up from the Philadelphia Navy Yard and try to help them weld these without a crack. And every time they were getting hydrogen cracks. And they've been working on this for 6 weeks, and they had never been able to get a test weld that didn't crack. And so they were not going to be able to put this boiler back in the ship, and the ship wouldn't go very far without the boiler, right? So they called me up one night and they said, if we use Inconel, we don't get cracks. And we need you to come in and tell the Navy why it's okay to use Inconel rather than stainless steel. So I go up to the library in Building 10 right before I go home, and I look up a paper in the Welding Journal back in the 1960s, which back then wasn't that much earlier. And it basically said that the long-term creep behavior of these joints, if you use stainless steel, is very good. If you use Inconel, it wasn't so good. Okay? So I wasn't going to be able to, I mean, there was a good technical reason why the Navy said use stainless steel and not Inconel inserts. So I went in the next day, and I thought I was just going to meet with 1 or 2 guys. I was a young assistant professor. I hadn't done much consulting. And there were about 10 guys there. There was the foreman, and there was the welder, and there was the engineer, and there was the shipyard manager, and they all come in, and I'm supposed to, you know, I'm 28 years old, right? I didn't have much gray hair then, and I looked young and unknowledgeable and all those other things. And they said, well, we want to use Inconel. I said, well, you know, there's this paper that, you know, long-term performance says you can't. Well, what do we do? And I said, well, what are you doing? And they explained what they were doing. And all I knew was that I had these 3 things to play with, right? Well, I knew that the chrome moly steel is the chrome moly steel, and there's nothing you can do about the hardenability of the chrome moly steel. I knew that, I asked them about what process. They were using gas tungsten arc, which is the lowest hydrogen process. This was probably just moisture in the air, got a little bit of train, but they were already using the lowest hydrogen process. So this one was down as low as they could get. This one is about as bad as you could get, but that was the nature of the material you were welding. And the only thing I could do anything with was stress. And I thought, well, their old joint preparation was a joint like this that had a little land. You put the EB insert down here. I didn't draw it. It's precisely over there. Put the EB insert down in here. And I said, well, change that joint design. Make a J groove with a long land like this. And put your EB insert in here. And make your root pass right there, so this thing is not as stiff, okay? Get some flexibility. Get rid of some of the stress on that root pass. And I said, try that. And I started walking for the door when to get out. And they said, no, wait, we'll do it while you wait. Oh, great. So we go out, and this foreman mills the end, you know, puts it on the lathe, and he turns it on the lathe, and he said, well, is that long enough? I said, oh, no, make it a little bit longer. So I had to make it like a 1/4 inch length. This is pretty big, you know. So now we have a thin wall pipe, a thick wall pipe, where we're going to put this root pass. And so they put the EB insert in there, and the welder welds it up. And these steels have to cool very slowly. One of the things I haven't talked about, you can preheat, you can post heat. And what they did is they wrapped it in, back then, well, I don't know, 1978, it may not have been an asbestos blanket, but a fire blanket. We had to wait a half an hour while this thing cools in the insulated blanket, because you want to slow down the cooling rate to allow the hydrogen time to diffuse away. But they had been doing that, okay? And that wasn't anything new. And the whole time the foreman said, this isn't going to work, this isn't going to work, okay? So we decided, after half an hour, they decided it's cool enough, and I'm standing around, everybody's standing around, just waiting, right? Fortunately, I'm going for this. So then they take it out, and they're going to dye check it to see if there's a crack. And to dye check it, you first clean it off with this solvent in a spray can, and then you spray it with this red stuff, this red goo. We'll go over this next time. And the red goo goes into the crack if you have a crack, but you have to leave it there for 10 minutes. So we waited a half an hour for it to cool, another 10 minutes for this. And the whole time the foreman, this is not going to work, this is not going to work. And then you clean off the red goo with some of the solvent again, but the stuff down the crack won't be cleaned out because the crack's so thin. And then you take it and you spray on this white developer that picks up the red goo will come out of the crack into the white developer. So some of you have probably seen dye check before. And so here's the foreman. He's twisting it and spraying it with the developer. No crack. So I walked out as a hero. I could have walked out as, the unknowledgeable 28-year-old kid. I didn't really know it was going to work. I mean, there is no equation anybody can give you that says this is what you need to do to solve a hydrogen crack. All I knew is that they were already doing as much as they could possibly do here. I didn't know another process that they could go and do the ship that had lower hydrogen. This is what the boiler was made out of. There wasn't anything I could do there. The only thing I could work on was this. And I just had to make the joint more compliant. Well, it's not rocket science to say that's a less compliant joint, or there's a more compliant joint than that one. And it worked. So I walked out as a hero. 2 years later, the shipyard's out of business. Not because of that, but anyway. So sometimes you just have to have the guts of your convictions. Although I would have much rather just left and had them call me back to say it was successful, or call me back and say it didn't work. But no, I had to stand there and ignore this guy yelling at me that not going to work. Talking a little bit more about these types of hydrogen cracks still occur. The problem with the Seawolf submarine, going back to this Venn diagram, was basically the main cause. They were welding HY100 steel, and they had a gas metal arc welding electrode that has specific chemistry composition range. I don't remember, but it might have been, the carbon content might be 10 to 16, and the manganese might be 1.6 to 2.0. I don't use these numbers, okay, but in any of these things, these are types of ranges you would have for your chemical composition. And then you have nickel, and chrome, and moly, and all these things. Well, it turns out they had done a bunch of their testing and qualification procedures on some electrodes that were kind of in the middle of the range. But when they actually started welding the Seawolf submarine, they happened to get a heat of wire that was on the high side of the range. It had more alloying elements, and the more alloying elements, the harder the microstructure. And so it turns out they were shooting for a weld metal that had a yield strength of like 110 KSI, because you're welding 100 KSI material. You want your weld metal to be stronger than your base metal, so that the strains are distributed through the base metal rather than concentrated in the weld if you actually get de-yielding. Okay? So you always want overmatched weld metal, higher strength weld metal, but you don't want it a lot stronger. Well, it turns out for most of the cooling rates they were getting, they were actually on the high side chemistry range, which they never tested in the laboratory. They were getting more like 130 or even 135, in some cases 140 KSI yield strength in the weld metal. They had up to 30% higher strength here than they had ever expected. They had done their tests on something that was 25% less, right? 30% greater, 25% less, something like that. The hydrogen, we'll talk about that in a second. The stress level, it was HY80 or HY100, so the stresses were up from HY80. But they had done tests and they thought they were okay. Turns out the hydrogen, there were 6 people brought in by the chief engineer of the Navy to kind of look over electric boat's shoulder, and I was one of those, and each of us had to write an independent report. In my report, we didn't have a lot of data. Electric boat had been measuring things. They found on the electrodes that they had 3 32nd diameter electrodes, 16th inch and 045, three standard different sizes of electrodes. I took the data we had, which is like 20 data points on each one of these or so, for hydrogen on the electrode. I showed that you got higher hydrogen contents as you went to smaller diameters. And from that, I inferred it was likely that they had contamination of lubricant, which contains hydrogen, on their electrodes. These people, have to draw the wire, you have to draw it through a die, and it has lubricant on it. You're supposed to clean it off. But I concluded, since I was seeing an effect of hydrogen content with wire size, it was a surface volume effect. And smaller wires have more surface area per unit volume. And I concluded that they had extra hydrogen because the wires were not clean enough. Okay? I was the only person who concluded that. Of course, I was also the only person who tried putting numbers on anything. But they ended up with all these little micro hydrogen cracks throughout the weld metal in the Seawolf submarine. The hull was 18% complete, and they had to start all over again. Okay, that's enough. We're running over a little bit. We'll take the break, and I'll finish up on the Seawolf after the break. People from Lincoln Electric and Southern Electrodes were very upset with that opinion. I don't think it was wrong, but and the stress levels were potentially a little bit higher just because the weld metal strength was a little bit higher. Essentially, they were not substantially higher. I think I mentioned before the way they discovered these cracks were very small cracks, and the way that it was discovered is a grinder was grinding the reinforcement off the weld on the inside of the hull because it needs to be smooth, and he noticed that the grinding swarf, the little metal powders, the iron, the metallic iron filings, were not just kind of falling off uniformly. Some of them they were kind of aligning. He was essentially doing a magnetic particle inspection. Steel, submarine gets a little magnetism to it, and they will line up with the cracks. That's actually the type of thing. And it didn't, the pattern of the grinding particles, not the grinding particles, but the metal powders produced by grinding was unusual to him, and so he reported to somebody. And so someone went in there, and they did much more careful non-destructive testing than they had done before. Before, you were looking for big cracks. Typically, what will happen in hydrogen cracking is delayed cracking. It won't show up immediately. 4 or 8 hours later in a big heavy weldment, what people found in the 1960s when they were first welding HY80, they went to higher strength submarine steels, is they might weld something on the day shift, and the people on the night shift would hear this thing like a cannon going off, and it was basically a crack popping in. It got stripped in size, and then it ran for 10 feet or something, or 5 feet, or whatever the length was. And it goes off like a shotgun because it's releasing all this pent-up residual stress, okay, in the structure. So you didn't have a hard time finding them. You knew if you had someone there 24 hours a day, you could hear the cracks when they let go. It turns out the shipyard has a specification that you wait before doing your non-destructive testing to ensure that the hydrogen cracks, if they're going to form, have had time to form. Hydrogen cracks do not generally form after more than about 48 hours. However, in a big 4-inch thick weldment, it takes a lot of time for the hydrogen to diffuse out. And in fact, in the Seawolf remedial action, there's several things you can do to help get the hydrogen out. You can preheat the steel. You can post-heat the steel. You can stress relieve it afterwards, or you can peen, which means hammering on the surface to change the stresses. You're trying to work on different ones of these. Preheating you basically are heating up the steel ahead of time so that when it cools down, it will cool down more slowly because it's starting at a higher temperature to begin with, and so it's going to cool more slowly as it gets towards room temperature because it's already heated. It will also take longer, as it cools more slowly, that gives more time for the hydrogen to diffuse out because it's coming out just like the CO2 in your soda. And at a high temperature, the CO2 in your soda, if you boiled your soda, you get the CO2 out as soon as it hits the boiling temperature, right? Boiled water doesn't have a lot of dissolved gases. Well, same thing, hot steel allows hydrogen to diffuse out. Typically 200 or 300 degrees Fahrenheit is all you need. In some steels, depending on the thickness and everything else, I'll tell you how to figure all this out in a second. You may only need 50 degrees or 100 degrees. The ASME boiler and pressure vessel code says you shall not weld on steel that is at a temperature of less than 50 degrees Fahrenheit. Now the reason for that is because steel gets down less than 50 degrees Fahrenheit, you can start to form dew, condensation on it, so you're welding it. You may not see moisture, but you could have a layer of moisture that you're welding over, condensation on the surface. Or if you get below 32, you actually get frost on the steel. You shouldn't weld over frost, not a good idea. Okay? Frost contains moisture. You can post-heat the steel to even slow the cooling rate down more. You can stress relieve the steel, typically 1 hour per inch of thickness at 1100 to 1200 degrees Fahrenheit. For great big pressure vessels, they have furnaces that are 10 times the size of this room. And they also, in some cases, will build the furnace around the vessel. So there are vessels that are even bigger than 10 times the size of this room. They build a furnace around it and they heat it up to 1200 degrees in the field. Okay? It takes a fair amount of power to do this. It's not a cheap process, but it's better than having your vessel blow up on you when you're stressing. Okay? You can peen the steel, which basically means you go in there after you make a pass and you hammer the surface to introduce surface compressive residual stresses to eliminate your mechanically stress relieving by peening. We believe that's how they welded the armor plate in World War II, but I told you before, we don't know how they weld 10-inch, 14-inch thick steel anymore. We don't do it. And when the battleship was the island, you said, had the problem, they didn't repair parts of that because no one knew how to weld steel that thickness. So we use all of these. Now, how do you know which one to use? Well, it depends on the composition of the steel. The hardenability of the steel is a function of the alloying content, and we get that down to what we call a carbon equivalent. You don't have to remember this. You have a hard copy of this in your notes. And the video doesn't really have to get this, but there's all kinds of formulas. This sheet comes out of a book I'll show you in a second. But there's lots of different formulas for carbon equivalent equals the carbon content plus the manganese over the 6 plus the chromium, molybdenum, and vanadium content divided by 5 plus the nickel and copper divided by 15. And here's another one that includes vanadium and silicon. And here's another. There are literally dozens of these formulas, all empirically derived by people welding steels and saying which one's cracked and which one's didn't, based on the steel chemistry. The advantage of going to accelerated cooling, control rolled steels and things, some of these steels they produce in Japan and Korea now, and we can produce some of them in the United States, we don't do too much of it, are almost uncrackable by hydrogen cracking. Okay? That's not true of your Martin City quenched and tempered HY80, HY100, or HY130, depending on whatever is foolish enough to use it. So we have to either eliminate the hydrogen or eliminate the stress. And those are the techniques we use. That particular sheet came out of the back of this book, Introduction to the Physical Metallurgy of Welding by Kenneth Easterling. This book also has this story, which I think I copied for you, the case of the Alexander Keelan disaster. This is the offshore platform in the North Sea. March 27th of March 1980, the Keelan, 6:30 p.m., tipped over the North Sea. 123 out of 212 people on board died. It was a hydrogen crack at a 6mm, a quarter-inch fillet weld. That started a fatigue crack that got to be tens of feet long before the thing finally came apart. Supposedly divers the week before had inspected that area. Now, sometimes it's easier to just say you inspected it rather than actually do it, right? But, you know, it's kind of messy to have to dive in the cold water and stuff, you know. It's not as if they didn't have inspection procedures that should have caught it. But, you know, usually when something occurs, when something goes wrong, not usually, but many times there's more than one thing that went wrong, okay? The shipyard shouldn't have welded a high carbon steel, you know, it's like a 0.6 carbon steel. That's terrible. Okay, they didn't control the quality of the steel they were welding. At the shipyard, they developed a crack. The diver should have caught the crack. You know, there's multiple things to wrong. Now, about 2 or 3 times a year, I get a call from some architect or engineer in the Boston area saying, we're repairing a building down here in Boston, or a bridge or something, or we got a penstock up in Maine. What's a penstock? You might know what a penstock is. A penstock is basically in hydroelectric plants where you want to bring the water down the mountain to an electric, to a generating facility. The big pipe they bring the water down the mountain on is called a penstock. I don't know why. I've never figured out why they call them penstocks, but they go back. In the old days, they used to make wooden penstocks, and they bring the water down wooden penstocks. But you don't have to come down more than 1,000 feet. How much pressure are you going to develop in 1,000 feet? For fresh water, it's going to be about 40 pounds for fresh water, 0.44 pounds per foot for seawater or so. So let's say it's 40 pounds, so you got 400 psi. Well, you don't necessarily want to, you know, if you drill out a log to make a pipe out of it, you don't necessarily want to pressurize that to 400 psi, so it'll split overnight. But hey, the old penstocks, they used to have steel bands around wooden logs that had the centers bored out. But some of these penstocks will, you'll have a 2,000 foot drop, you got 800 psi. And some of these things are big. I worked on one that was 22 foot diameter pipe, high Sierras, about 9,000 feet. And it had a hydrogen crack around a manway because the boiling pressure vessel code, 1 1/4 thick steel around a manhole, was supposed to be stress relieved. But they were doing this welding just after Thanksgiving, the week after Thanksgiving in the High Sierra. The snows had started in September. We think they were welding on top of steel-coated pipe, snow-coated pipe. So they didn't, even if they were preheating on one side, it's not clear how long it was lasting if the snow was on the top side of the pipe, because they were welding overhead on this thing. Anyway, there was a flaw, about 3/8 of an inch deep, about 2 or 3 inches long. And 8 months later, after the snows, they actually left a week after they finished this, which is one of the reasons we don't think it's stress relieved. In fact, there are no records that they stress relieved, and there should be. So they didn't stress relieve it, it had residual stresses. They loaded it up with water at 188 psi, and 18 hours later, it blows apart. And there were eyewitnesses. There were a couple of guys in the canyon. They were cutting firewood when the thing let go. When it let go, 4 million horsepower coming out of this thing. The upper lake dropped by 50%. It took them a half an hour to close the valve up there. I mean, 22 foot diameter valves are not things you just kind of torque with your wrist. And they actually had to get to it. There was a 100-foot granite cliff, 100 feet high, and water coming out across this little canyon at 188 psi, 22 foot diameter pipe, eroded away an extra 100 feet of canyon wall. We just moved the canyon wall 100 feet back in that half hour. It built a sandbar about the length of a football field down at the other lake. It's sort of an exciting failure. I wasn't there to see it, but I mean, just even being up there to visit it, the site was sort of impressive. But it was all because of a hydrogen crack, failure, stress relief, not following the proper procedures. If you want to know what the procedures are, when I get a call from these companies, they say, we got a 100-year-old building here in Boston, we got a weld to this thing as we're doing this remodeling on the building. What do? I say, get me a piece of steel. It'd be best if I can do a hardness on it, but I don't have to do that. I need the chemical composition of the steel. If I have the chemical composition of the steel, I go to this handy-dandy book called Weldability of Steels, 4th edition, by Stout and Doty. This is 1987, which is the most recent. But they have in the back an appendix which lists for 208 different steels what the welding procedure is. And if you go to this little table, it tells you for what thickness steel, or for what carbon content, what thickness, 1 inch, 2 inch, 3 inch, 4 inch, what the minimum preheat temperature should be if you're using a low hydrogen electrode, or whether you're using other than low hydrogen, which means cellulosic. It will tell you if you need to do post-weld heat treatment. It will tell you whether you need to do peening. Okay, it will tell you what the minimum preheat temperature should be. So basically, these are the things that you have to do on these things. It will tell you if you have to stress relieve. It will tell you what those things are. And so basically, they give me a chemistry. I have to go find the steel with approximately the same chemistry. Look in here, and it tells me. You can say it's somewhat empirical. People have developed all kinds of formulas that try to relate these things back to the weldability of the material. To give you an idea, on the Seawolf submarine, they had the high side chemistry. Well, they went to the lower side chemistry, but they couldn't afford with Congress after a $400 million hiccup to have a failure the second time, because then it would have canceled the whole program, right? So they basically went to like 400-degree Fahrenheit preheats. It took for the first year. Okay, now 400 Fahrenheit preheat. You start thinking of the submarine, the nature. They had people welding in what they called blue jelly suits. Anybody know about the blue jelly suits? Okay. They basically, if you had to go inside one of these A-crate construction type of foundations, you're going into a 400-degree oven. And so they basically had the welders put on these suits that had this blue gel in them. And they were pumping fluid through. They were in an air-conditioned suit, if you will. And they would go inside in this 400-degree oven, and they would weld. And they were only allowed to be in there for about 10 minutes before their lungs would start to cook anyway, just from the hot air. So they allowed about 10 minutes worth of welding. And they, a lot of times they were on little carts, little railroad tracks, so that if something happened, they could pull them out quickly, things like that. So they were monitoring them and stuff. It's really exciting. It's also real cheap, as you can imagine, to do all this extra control. So you try to do something in the shipyard where your preheat's never get above about 150 degrees. Because what's the big deal? The guy has to go out there and weld in 150 degree temperatures, right? It's a big deal to him. It's not that comfortable in the summer. Not even that comfortable in the winter at 150 degrees. Might feel good at first, but they went to some extreme things until over that next year they did enough research to figure out exactly how far they could lower the preheat and other things. Initially, to get back in business after about 3 or 4 months of being out of business, which was kind of pricey itself, they basically went to very high preheats, well above anything that anyone would think might be harmful, or any level that anyone thought might be required, just to be able to be sure they didn't have a problem. And not everyone, they didn't have to weld everything in blue jelly suits, but you're welding some of the heavier material in some work confined spaces, and they had people welding in blue jelly suits. So, let's see, other failures of note. I guess I can't think of any other hydrogen failures of note. To give you an idea of hydrogen failures, it's also important just in heat treating steel. So let's say a helicopter rotor mast. I know one helicopter company that requires, from when you quench and temper the helicopter rotor mast, which is 4340 steel, has a strength of 180 KSI yield. They require that you go directly from the tempering furnace into the hydrogen bake-out furnace with as little time as possible, so you don't get a hydrogen crack. Now, that's sort of extreme. I've never seen anyone else do it quite that way. But there is now an ASTM spec that says when you're heat treating high-strength steel parts, this is not welded parts necessarily, if you're heat treating them, you quench them, you temper them, and then you're supposed to give them a bake-out at 325 degrees Fahrenheit, either after, if you electroplate them with zinc or cadmium or something like that, that can introduce hydrogen. They must, from the time you finish the electroplating or the tempering operation, you must put them in the furnace within 1 to 4 hours, is what the ASTM spec says. That's because hydrogen is delayed cracking. You delay any longer, it's too late to prevent the cracking. The crack may have formed in those 1 to 4 hours. Usually the cracks will occur in a couple of days. They don't last for years. I had one guy on a helicopter crash claimed the bolt failed from hydrogen embrittlement from manufacturer 8 years later. I call it the Rip Van Winkle theory of hydrogen embrittlement. The hydrogen went to sleep for 8 years, woke up, decided to do his damage. That's ridiculous, okay? Hydrogen embrittlement usually occurs in a very short period of time. There are some cases where welds have porosity that can trap hydrogen for long periods of time, like 6 months. It's trapped in the pores. I had an example of that not too long ago. What was that? It was a sintered metal part that went in the gas meter. And the sintered metal part starts out with metal powders, and they typically will heat treat that to condense the metal powders. And then this is the gears in your automotive transmission are made out of iron powder parts. They typically will sinter that by heating it in a hydrogen-containing atmosphere. Well, it turns out that's okay because usually these are not such super high-strength parts, but the hydrogen is now trapped inside a pore as molecular hydrogen H2. The hydrogen that does the damage is atomic hydrogen H, not H2. And so you can actually store hydrogen in a steel tank and it will not diffuse into the steel unless you give it some energy by electrodeposition voltage or temperature of a plasma or something like that. It's the monatomic hydrogen that wants to go in there. It's not the diatomic hydrogen. So if I actually have some porosity, in this case the sintered metal parts were only centered to about 90% density, and so 10% of them were just little hydrogen tanks. And then they put this hardened steel pin, roll pin in here, and it cracked the roll pin. And they were blaming the roll pins for being defective, when in fact it wasn't the roll pins that were defective, it was basically the steel part that they were going into contained hydrogen. The stressing caused some of the hydrogen to get out of that part into the hard steel part then cracked. Whereas the actual part that was holding it, that contained the hydrogen, was a low-strength steel, didn't have very high stresses, but when you put this hardened steel roll pin inside the hole, under stress, it cracked. So in that case, the hydrogen may have remained there for a few weeks or even a couple of months under those conditions. The hydrogen usually it will relieve itself over time. Any other examples of hydrogen? So you have to look at each thing on its own merits. But in general, the hydrogen cracking occurs within a few hours or at most a few days. Okay? Hydrogen cracking is the big problem in steels. Not to say there aren't other problems. In fact, I brought a little book. If I can find it. Unless I left it on my desk. Little pamphlet. Here it is. Faults in fusion welds and construction of steels put out by the Welding Institute. It shows you all types of cracking and porosity. The first is solidification cracking, unless you got really dirty steel or you're welding over paint, which is sometimes in shipyards, you don't usually get that type of cracking. The next one they list is hydrogen cracking. Surprise, surprise. Hydrogen-induced weld metal cracking was the third one. Lamellar tearing, which is kind of a tearing in the base metal. The steel plate's rolled, it gets the texture kind of like wood, and the hydrogen will go down. This is another type of hydrogen-induced cracking. It goes down and basically splits the material along the planes, and you get a woody type of texture to the fracture because the rolled steel has soft planes in it, like the texture of the steel. Reheat cracking, which turns out to be another form of hydrogen cracking. When you were doing stress relief and you heat it up, you can get cracking. Then they start getting into cavities and porosity, slag inclusions, and they get into other types of defects such as too much weld reinforcement, too little weld reinforcement, excessive bead penetration, which are geometric stress concentrators and things. But if you look in there, most of the cracking, although there's several different names, relates back to hydrogen. So when you're welding steels, you should be careful about the hydrogen cracking problem. Any questions on welding steel? If not, we'll go to aluminum, another metal. Whereas the guy used to be in charge of research at US Steel called aluminum the near metal. Of course, he had sort of a bias against aluminum, but nonetheless. Aluminum comes in lots of different alloys as the steel, but the aluminum alloys are a little bit easier to categorize, maybe because there are not quite so many of them. And maybe because there are the 1,000 series aluminum alloys, the 2,000 series, the 3,000, 4,000, going all the way up to the 8,000 series and the 9,000 series, I guess. What a clever designation. Well, 1,100 aluminum is basically pure aluminum. If you own an aluminum frying pan at home, it's probably 1,100 aluminum, which means it's 99% aluminum and 1% something. And that something is not usually intentional, it's just kind of the general purity. 1050 and 1060 is 99.4% aluminum, I think. 99.6% aluminum, and 1050 is 99.5% aluminum. You go all the way over here, you don't have to worry about these things. And these are basically electrical conductor grade of aluminum. You get to the, well, this doesn't list the 2000 series, because these are the non-heat treatable alloys. The 2000 series are aluminum copper alloys. The 3000 series are aluminum manganese alloys. Aluminum manganese alloys are actually the highest volume production of aluminum alloys. Anybody guess why? Beer can stock. 40% of all aluminum goes into soda cans and beer cans packaging. So 3003 or 3004 is basically 99% aluminum, 1% manganese or so. Let's see what it says. It says 1 to 1.5% manganese for 3003 to 3004. Very easy to draw. The manganese gives us a little bit of strength. The 4000 series are aluminum silicon alloys, primarily used for welding. I don't know base metals here. I do know cast alloys that would be in that range. The 5000 series are aluminum magnesium alloys, and essentially get their strength by just solid solution strengthening with 5% or so magnesium in there. The 6000 series alloys, which are not on there, basically are aluminum magnesium silicon, and they're heat treatable. And the most common alloy in that grade is 6061. You often hear about 6061 T6. And the aluminum alloys, they go by a 4-letter designation, depending on whether the 1000, 2000, and 3000 series. And then they put a T number afterwards. So if I have 6061, this tells me a specific composition, and I have to go to the Aluminum Association to see what that specific chemistry is. But then I put T6, which means it was tempered under condition 6, which means artificially aged, quenched and tempered, quenched and artificially aged in the furnace. Aluminum alloys, the heat treatable aluminum alloys, what happens, most aluminum alloys have a phase diagram. When you take pure aluminum and you mix it with something else, you often get a eutectic, whether this is copper or magnesium or silicon or zinc or a number of other things. If I heat this is liquid, this is solid, face-centered cubic aluminum, and then I'll have some precipitate over here, which might be aluminum copper, aluminum magnesium, or aluminum silicon, intermetallic. If I heat it up to this temperature range, this is liquid plus solid here, and this is solid, I'm still in the solid range, I can dissolve everything into single phase. If I then quench it and drop the temperature and hold it at I can quench it all the way down to room temperature, and then bring it back up to some intermediate temperature, I can precipitate out, because this is the solid plus intermetallic. I can precipitate out these little fine intermetallics which strengthen the aluminum. And I can double the strength of the aluminum by heat treating it. And that's wonderful. That was discovered in the 1920s. To give you a history of aluminum, I told you that aluminum used to be more valuable than gold. I told you that story, right? The top of the Washington Monument was made out of aluminum because it was more valuable than gold. And 3 years later, Charles Martin Hall came around and turned it into a commodity by coming up with a process of refining aluminum from its ore, such that now 7% of electricity in the United States, actually not anymore, but 20 years ago, 7% of electricity in this country was used to produce aluminum. Now they do it in Venezuela and Norway and Canada, where they have cheap hydroelectric power. And actually, the former Soviet Union is the one who really killed the aluminum industry in this country, because they don't care. Aluminum is canned electricity, right? It's just, you can ship aluminum ingots, and it's like shipping electricity or energy. There's so much energy content in that, refining that aluminum, that the value of that aluminum, the $1 or $2 a pound that you're going to pay for the aluminum, half of that value is the cost of the energy to refine it into the metallic state. And so, you know, the former Soviet Union has these energy reserves, but how do you get the energy to somewhere where someone needs it? Well, you turn it into aluminum and sell them aluminum. So the price of aluminum dropped to below 50 cents a pound when the Soviet Union broke up and they started dumping their capacity on the rest of the world. In any case, you can double the strength of the aluminum if you go to these heat-treatable alloys. And so Charles Martin Hall came along in 1889, formed Alcoa, Aluminum Company of America. They had to divest Alcan, Aluminum Company of Canada. They were all one company once, but the government forced them to divest. They're now the 1 and 2 largest aluminum companies in the world. Okay? Actually, it's interesting if you go back to learn some of the history of some of these companies. Anyone know what Boeing, United Airlines, and Pratt & Whitney all have in common? They're all the same company originally. Okay? I mean, you know that Standard Oil Rockefeller was broken up, and you know that U.S. Steel and some others were broken up by the trust busters. But if you actually go back and look at what happened in the 1910s and 1920s, there were a number of other companies that were broken up. Boeing, United Airlines, and Pratt & Whitney were all one company originally, as far as that goes. Alcan and Alcoa were one company. In any case, getting back to the aluminum metallurgy, in the 1920s, people learned that you could heat treat these aluminum alloys and get high strength. They actually learned it a little bit earlier than that. These aluminum alloys will actually continue to age even at room temperature. One of the heat treatments, I think it might be the T3 heat treatment, is not artificially aged in a furnace at higher temperatures. It just naturally ages at room temperature. The precipitates will form at room temperature. And so I told you that the Concorde flies on temperature, you know, the supersonic transport. The skin gets too hot and it's going to overage these aluminum precipitates, and they won't have the strength and they'll have to ground it. So they limit the temperature. There is one experiment that's been run for about 100 years on a heat treating of an aluminum alloy. It's named, if you go to the Smithsonian, they have the Wright brothers engine, and it was a cast aluminum engine, and it was an aluminum copper alloy. And about 6 or 7 years ago, some people at the National Institute of Standards and Technology took a piece of that engine, cut it out, and did work in the electron microscope to look at the aluminum copper precipitates, which had been aging for 100 years at room temperature. So they actually plotted it up and showed it. It fit the data. You know, they did data for 1 day, a week, and a month, you know, and then they showed on a log scale, if you go out here to 100 years, what they saw in the Wright brothers, the size of the precipitates now 100 years later is exactly what they would have predicted based on the other data. Okay. So these precipitates form and give you twice the strength. So you go to the 7000 series, which is zinc alloys, and 7075 was the old workhorse alloy 25 years ago in the aircraft industry. A lot of 7075. Another one in the aircraft industry is 2024, which is 20 aluminum copper alloy, not weldable. Will crack every time you weld it. Start off fusion welded. There are other aluminum. In fact, the aluminum copper alloys are generally considered not weldable. But to prove the exception to the rule, the space shuttle is made out of 2219, which is an aluminum copper alloy. But it is designed to be weldable, but not very weldable. Okay. But they go to it because they get tremendous strength. And in the space shuttle, what's the value of pound saved in the space shuttle? 10,000. Actually, it's 10,000 in the space shuttle. rocket is about 20,000. Space shuttle gets that cost down by a factor of 2. So NASA will pay a lot, and in fact, there's a new type of welding process, the only new one in the last 25 years by my reckoning, really new one, called friction stir welding. And this is a NASA plate, friction stir welded at Marshall Space Flight Center out of 2195, with aluminum copper alloy. And basically what they do is they take a steel or stainless steel rod and they spin it, and they just kind of plow right through the aluminum. If you look on the backside, you can see a little line, which was the joint. And they basically solid state weld this by frictional heating. And it leaves a lousy surface, which of course they've milled off, because this is something NASA's going to give away to people, tell them why they spent $100 million on this process. Right? So you don't want to see a piece of that looks like a dog's breakfast sitting on top of the plate. But Boeing just put in a line for $100 million. And the great thing about this is you'll notice there's no distortion here. You didn't melt the aluminum, and so it didn't shrink on solidification with the 6% volume change that causes so much distortion in aluminum. And that's very important for something like the space shuttle. The only problem with this is you have to have an anvil to weld on, because you're basically plowing your way through solid aluminum as you're spinning this. This mandrel through it to make the friction stir weld. But that's kind of what everybody in the pet dog is out trying to do research on now, which is one of the reasons I wouldn't touch it with a 10-foot pole.
You end up having a bunch of stresses on either side of it.
The stresses are less because you're still solid state. I mean, in the solid state, yeah, yes, there will be residual stresses there, no question about it. But they're going to probably be 1/3 of what they would be when you actually do fusion welding. Fusion welding, there's 6% volume change on solidification. Here, there might be a volume change, but it might be 2 or 3%. Even though it gets hot, okay? I mean, the material gets hot, it changes its microstructure, but if you look in a microscope, you will not see any of that melting.
I was just thinking it was shear.
No, there will be residual stresses, but they'll still be much lower than that. The really big residual stresses come from all this shrinkage on solidification, okay? So that's the problem. Now, the key on aluminum, or one of the keys in aluminum welding is the same type of diagram. The aluminum alloys, because they have this liquid plus solid, and then solid plus another solid over here. This is the mushy region. This is your snow cone. This is your Slurpee. Okay? It's partial liquid and partial solid. It doesn't have great mechanical strength. Of course, the liquid doesn't have any strength at all. But the problem is, if what happens in aluminum alloys, I can weld the alloys that exist over here, because the freezing range is fairly narrow on cooling down. I can weld the alloys that exist over here because the freezing range in here is fairly narrow. Here I have a huge freezing range, and these will crack as I try to solidify them, because if I make a fusion weld and the thing's starting to solidify, I've got a whole range of temperatures, but I have to absorb this much thermal strength, delta T times the 6% volume expansion, bigger delta T here than over here or over here. So if I'm going to weld an aluminum alloy, and these alloys come in all kinds of shapes and varieties, in terms of some of them have a 10% alloying element, others have only a few percent alloying element. You don't find a lot of them that only have 5% alloying element, because they're just not going to be weldable. They're not even going to be very castable. You've got to either be very lean in your alloy or very rich in your alloy. You don't want to be intermediate in your alloy. And one of the problems that you sometimes run into, if someone doesn't know what they're doing in welding aluminum, they will pick a filler metal, an aluminum wire, that's not compatible with the alloy they're welding. If I'm welding a highly alloyed aluminum, I better use a highly alloyed wire. Because if I use a lightly alloyed wire, I'm liable to end up with a freezing range in weld metal that's right where I don't want to be. So it turns out, if you go to a book on welding aluminum, such as this, by Kaiser, they will have charts, and I'm not going to show you a specific chart necessarily, but they will tell you with a specific aluminum alloy, or two different alloys you're welding together, what welding electrode you can use. You can't just use any old welding electrode. You have to use one that's designed for that combination. So there are dozens of aluminum welding electrodes, and it all gets down to the fact of you want to avoid this intermediate range where you have a wide range of freezing. You want to keep your freezing range as narrow as practical to avoid the cracking problems. That's solidification current. The thing just kind of pulls itself apart while it's hot. Now the Navy typically uses aluminum alloys that are not heat treatable when they're trying to build hulls, such as catamarans or something else where they have to go to get lightweight. They typically use the 5000 series aluminum alloys. Those alloys don't have anywhere near the strength of these 60, 61, 75 aerospace alloys. And the problem with these alloys is you just can't get the strength when you weld them, because you're going to wipe out all this heat treatment that gave you the high strength. All these intermetallics, these little aluminum copper particles or whatever, are going to coarsen, they're going to overheat treat, and you're going to lose the strength that you were trying to get from that part of the process. To give you an example, a few years ago, this had to be back in the 1980s, because I'm thinking which office I was in at the time, probably somewhere between 85 and 90. I got a phone call from Raytheon over here in Waltham, and they were building parts for the Phalanx missile system. Phalanx is a missile system. It's a missile protection. It's basically a fire control system to shoot down incoming missiles, right? Yeah. So it's just a great big machine gun, right? So they were building the radar sets for the Phalanx, or where? Pardon? Yeah. It's not one you want to stand in front of, right? If it's fired. So it turns out they had built the frames that held all the electronics for this radar set and stuff out of 6061 aluminum. And one of the Navy inspectors was going through the shop, and he noticed that someone was using an oxyacetylene torch to heat up the aluminum and re-straighten it because it had been bent. He says, "Where's your procedure on that?" They didn't have a procedure for flame straightening aluminum. Now you can do this on most low strength steels. You can use a torch and you can heat it back up because, hey, the steel is rolled at 1300 degrees Fahrenheit. It doesn't care about you're heating it up to 1100. Okay, it was done at higher temperatures. But one of these alloys that's heat treated in these other ranges, you're going to lose some strength if you just heat it up in a furnace or with a torch without any control. And so I get this phone call because the Navy shut down the plant because no systems, basically all the workers just standing there, all the union employees sitting there twiddling their thumbs because the Navy said, "You can't do anything until we figure out, whether this stuff has got the right properties or not." So anyway, I come in and most of these systems were made out of I didn't draw it very well, but it was square, like 1.5-inch rod that had been welded together. Okay? And someone was just straightening one of these rods. So they're building frames that they're going to put big electrical things into. These are just the cabinets that this stuff is going to be put in. And so, actually, it's a little bit longer story than that. I just got back from a trip. I didn't have time to go over there. I said, "Why don't you call so-and-so? He's the newest Alcoa assistant professor. The Alcoa assistant professor ought to be able to tell you how to take care of your aluminum problem." And so he was a young professor. He didn't own a car. They sent a cab here to Cambridge to pick him up. He went out there, and I was busy with my meetings. And at the end of the day, I get a call from both him and from them saying, oh no, it was the next morning I got a call from them saying, "Can you come out?" Because he was the Alcoa professor, but he didn't know how to solve the aluminum problem. So I was busy that second day, and I said, "Look, I can't get out of here until 5:30 today. If you'll have someone there at 6 o'clock, I'll drop by at 6 o'clock because Waltham's sort of a little bit out of my way, but sort of in the same direction as going home. So I stopped by at 6 o'clock that evening. The plant's pretty empty because the workers who are being paid to do nothing for the last 2 days had all gone home. But the engineers are there. They take me out. They show me this, these frames, and I said, well, what's the weld look like? So they take me in and we look at drawings, and the welds were basically, they were not full penetration welds. Okay, but if I was looking at this in cross section, they would have a weld here and here. They weren't even trying to weld the center. So if I looked end on this whole thing, on a square, I might have welds along here, along here, along here, along here. And the center region wasn't welded at all. Okay? Now the problem was they were afraid they'd softened this and it no longer had the strength of the original stuff. And I said, well look, first of all, the heat effective zone here, when you're welding this, you lose half your strength. You overage, and the heat effective zone is always only about 50% stronger. If I make a welded 6061 bar, and I do a tensile test, it will fail in the heat effective zone and it will fail at half the strength of the base material. Because the heat from welding destroys all this good heat treatment I already did, and I no longer have these precipitates in the heat effective zone, and the heat effective zone is soft. So at first they had lost 1/2 their strength, whether the guy used a torch on this or not. The guy who designed this had to have been designing this not for strength, because if he was designed for strength, he wouldn't have welded 6061, not in this type of geometry. Then he wasn't looking for strength here, because he only had about 50% of the cross-section welded. So this was not a strength-limited design, and if you think about it, this was just holding electrical cabinets. It was like 1.5 inch bar material, just to hold a couple hundred pounds of electronics. And I said, this is not a strength-limited design, this is a deflection-limited design. Okay? And then you have to remember this, because most of what we teach you when we teach you mechanics is all strength-limited design. But there's half the design that's out there is deflection-limited design, where you just don't want things to sag on you too much. And so I said, this is deflection-limited design. I already lost half the strength in the welded part, but I'm only welding half the part, so this joint only has 1/4 of the strength of the base bar. And so I don't care as long as, and they had gone out by this time, they'd done hardness tests, they'd done tests on heating up bars with torches, and they had only lost about 30% of the strength due to these guys using torches when they weren't supposed to. And I said, well, you could have lost 75% of your strength, and you're still just as strong as that joint. In terms of strength, you don't have to worry about the strength. You don't have to worry about deflection. And the stiffness of this is basically the same as long as you haven't reached the yield strength that you have in the deflection-limited design. Right? So I had to write a letter, and within 72 hours after it started, they let them start making parts again. But the point of this is, when you're welding aluminum alloys, you can't get full strength. This person wasn't even trying to get full strength. But in addition, you could ask, well, why did they make it out of 6061 T6 to begin with? And this gets to the whole point of not every alloy is available in every form. If you call up a local supply center, and let's face it, if you're buying 100 tons of material, you can get whatever alloy you want in whatever size and shape that they produce. But if you're only making, a few tens of thousands of pounds of cabinets, and you call up the local metals place, they don't carry every alloy in every form. Turns out 6061 is probably the most common aluminum, higher strength aluminum alloy. If you want to get low strength aluminum, very low strength, you can get 1100 aluminum in lots of forms because of its good corrosion resistance. But if you want higher, anything with a little bit of strength, 6061 is available in virtually any form you want. Because this whole cabinet had bars, it had angles, it had tubes, it had all kinds of things in the design. So the designer had designed it out of 6061 because it was readily available, not because he needed strength. Okay? You have to understand some of these things that go on. And in that case, you have to think like a designer, which is not always easy to do, but nonetheless. So that's that example. Another example of heat-treated aluminum alloy I ran into, this is probably 20 years ago. There's a great big radar dish in Kwajalein Atoll in the middle of the Pacific. And this is, turns out, they put it in there for research purposes at MIT Lincoln Lab. But it turns out it had the right frequency and just the right location to be able to see the Soviet rocket shots from Kazakhstan and be able to predict the orbit while they're still in their boost stage before they actually got into orbit. So it turns out from like 1970 on, this became a critical piece of US hardware. And the replacement cost is like $2 or $3 billion for this thing. It's 100 meters across. The size of it, it's an aluminum dish the size of a football field. Okay? And so you can't afford to build another one. And in fact, whenever this thing was going to go down for repairs, it was classified. Okay? Because that's when the Soviets could send their missiles up, right? To put a new satellite in orbit or something. So, in any case, one of the first consulting jobs I ever got around here, like 1978 or so, had to do with the great big wheels that this thing rotates on a great big track. And actually, continue. This thing's been, it's now at 30 times its original design lifetime. Okay, this particular, in terms of how many revolutions it goes around its track and everything. It's outlived its original usefulness in years by like a factor of 2, but it's in terms of usefulness of how many revolutions it would go around and be turned around and look at the heavens and everything. It's at like 30 times its original design right now, and they have just extended this well beyond anything because they found it was such a valuable resource. Well, it turns out it has these 50-meter long aluminum tubes. They're like 4 or 5 feet diameter, which are these 4 of these things or 8 of these things or whatever, that basically hold the very big dish, right? And these were welded aluminum. And the original welder, or not original designer was a clever guy. He knew you stagger your welds. You don't put all your welds in line. And you've seen that on the hulls of ships, right? You don't stack up your welds like this, like a bunch of bricks. You stack them up, well, actually you wouldn't, but you stagger them so that you don't have a continuous line like that going straight through. Okay? Well, he knew that they had to take a aluminum plate and roll it into a cylinder, and so you have a longitudinal weld, and he had done some special reinforcement at the joints where they had to make their circumferential welds. But the guys using the aluminum plates used the biggest plates they could, and in order to make all these, they put a couple of other welds in between, circumferential welds, that were not in the original design. And so there was no reinforcement on those welds. And this thing had been in service for 20 years without any reinforcement on these aluminum welds that were in the main stress direction, right? Let's stress it this way. The longitudinal welds were not much of a problem. And so when they discovered this, someone noticed this, they took some samples and they brought me back a couple little samples, about this size, and they said, "What can you tell us about this?" And I was able to tell them quite a bit, it turns out. All we did was we took the weld, which might look like this, right, cross section, and we measured the hardness. So the hardness would be high hardness. No, wait a second. Let me move that. So let's look at it like this. You have high hardness in the base material. You have a lower hardness in the heat affected zone over here because it got overheated. And then the weld metal, the hardness would come back up, and then of course go down and stuff. So on a longitudinal weld that had never been stressed significantly, we measured the hardness profile that looked like this. On a circumferential weld, it was welded by the same process, we measured a hardness that looked like that. And the reason was, this one actually had been pulled and work hardened in service. It had taken very high loads. I was able to measure that hardness, convert it to an approximate strength, and tell them what the maximum load had been on that structure over the previous 20 years. How far it had been stretched, what was the maximum extension, based on the work hardening. And from that, they actually went back to look at their hurricane data, their calculations, and they were actually able to correlate whether their original design for hurricanes and everything else, which had been done in the 1950s when they didn't have fancy computers, was actually as good as they thought. So it turns out it wasn't a big problem. We actually found out what the maximum stress was, and they did go in there and they did reinforce these welds, so far as that goes. But they also had a data point that actually told them when the material had a memory of what the highest stress it had ever experienced was. And so, see, there's all kinds of little things you can get out of little pieces of trivia. I guess we've run out of time again. So I'll see you on Thursday and we'll finish up welding.